So the next deterministic model that we're interested in is the production order quantity model, the POQ. So we here it's used when inventory builds up over a period of time or after an order is placed, or I like to think of it more of it's used when units are being produced and sold simultaneously. So I'm producing and selling, which means I have to be producing faster than I'm selling. And basically what we're doing is we're taking the EOQ model and relaxing the third assumption. The third assumption was receipt of all the goods is instantaneous and complete. So here it's not instantaneous and complete. We're building up and selling at the same time. All right, so we're going to relax that assumption. So when we relax that assumption, our inventory level picture looks a little different. So instead of shooting straight up, we now have a slope, right? This is little t, which is the production run length, right? Where I'm selling faster than I'm producing, and so it's going up at that. And then I stop manufacturing that particular item, and then I only sell, so it goes down. I start the production process up again, right? Etc. Etc. So still kind of sawtoothy, but now instead of straight up like in the EOQ, it goes up at a slant. So here we have very similar stuff. Now what we've added is little p, the daily production rate, and little d, the daily demand rate. And so the production rate has to be faster than the demand rate or we'd never meet demand. And so we do the setup costs and the holding costs. Again, set them equal to each other. Solve for Q star. In this case, we'll try to use Q star sub P for POQ. It's the square root of 2ds divided by h times the quantity 1 minus d over p. So it looks very similar to EOQ. The difference is that little part in the denominator there. That's the part that's taking care of the production and selling at the same time. And if you want to work through the algebra, you can, but I'm not going to force you. So here's an example. We have 1,000 units for annual demand. The setup cost is $10. Holding cost is 50 cents per unit per year. We can produce 8 units per day. Demand is 4 units per day. I think we're selling hubcaps or something crazy like that. I don't know who buys hubcaps these days. Q star sub P is, we have the formula there. So we have everything. We can just plug it in. And we see that we get the square root of 80,000 again, which shouldn't surprise us too much. And we get 282.8 or approximately 283 hubcaps. So that's how many hubcaps we should produce for each production run. Every time we start up the process, Q star sub P is how many we should produce. Now, how long does it take me to produce 283 hubcaps? You should know that. Take 283 and divide by the production per day. That'll tell me how many days it takes me to produce it. That'll be little t. We could also calculate the costs, time between production runs, and all that fun stuff as well. I'm not going to get into that, but you might have a homework problem or something that looks at that. And then finally, our final deterministic model is quantity discount model. So what this is I buy in bulk, so I get a cheaper per unit price. So this is like going to Sam's Club, right? I can buy bulk paper towels cheaper per unit, but I have to have somewhere to store it. So the trade-off is reduced product cost, but increased holding costs because I got to have somewhere to put the stuff. So total cost this time is going to be setup cost plus holding cost plus product cost. So notice this time we are adding the product cost. Why did we not add the product cost for the other two models, EOQ and POQ? Well, it didn't change. So it wouldn't do anything, wouldn't make any difference. We didn't have to look at it. Here the product cost is going to change. So we need to make sure that it's accounted for in our total cost. Right? So here basically what we're doing is we're taking the EOQ model and relaxing only assumption number 4, quantity discounts are not allowed. Now they are allowed. Right? So a typical quantity discount schedule might look like this. Anything that I buy under 1,000 units, I don't get a discount. It costs me $5 per item. Between 1,000 and 2,000, I get a 4% discount, which equates to $4.80. Anything over 2,000, I get a 5% discount, which is $4.75. Right, so it might be in percentage, it might be basic, just a price. So we relax the fourth assumption of the EOQ model, and then we analyze by these 4 steps. Number 1, for each discount, calculate Q star. If Q star, step 2, if Q star for a discount does not qualify, choose the smallest possible order size to get the discount. And then step 3, compute the total cost for each Q star or the adjusted value from step 2. And then step 4 is the easy one, select the Q star that gives the lowest total cost. So why do we need to do the adjustment in step 2? So here are the different cost curves for something that we have order quantity on the x-axis, y-axis total cost. First price break, second price break. So we see total cost for discount 1, it falls as we would expect within that point, right? But something less than 1,000. When we calculate Q star for the second one, for the 1,000, we're going to use $4.80, not the $5. Well, the real Q star might be over here, and well, the problem is we don't get the discount over here, so we have to bump it up to the minimum to get the discount, which would be 1,000. And then the same thing could happen for the 3, so you can imagine this drops down here somewhere, right, where we have to bump it all the way out to 2,000. So again, it's below the allowable, so we have to move it over to point B. So here's an example. We calculate Q star for every discount. This time Q star, notice that instead of dividing by H in the denominator, we have I times P. I is a percentage and P is the per unit price, because a lot of times the holding cost will be based on the price of the unit or the value of the unit. So here it looks like we're doing toy cars. We have an annual demand of 5,000. We have a setup cost of 49 bucks. It's a 20% holding cost, and for the first point we're doing $5 right there is with no discount. We see 700 cars per order, which makes sense. It's less than 1,000 to get the next discount. Right. So for the second one, what we're going to do is all we have to do is change the $5 to $4.80 for that 4% discount that we were getting. And we see that it's about 714 cars per order. For Q star sub 3, we change it to the 5% to $4.75, which jumps up to 718 cars per order. So that's step 1. Step 2 says I don't get the $4.80, which I used to calculate Q star sub 2, until I order 1,000 cars, so I have to order 1,000. Same thing for Q star 3. I don't get the 475 for 718 cars. It has to be 2,000 cars. So those are the numbers 700, 1,000, 2,000 that we're going to use to calculate step 3, which is the total cost. Curves for each one. So we can see I've put it all out in a table. Maybe that's easy for you, maybe not. We see for the $5 no discount, order quantity was 700. Total product cost it was 5,000 times the $5, so $25,000. Ordering and ordering or setup and the holding cost are equal, so we're at 25,700. $4.80, so the product cost dropped by $1,000. Ordering cost dropped and holding cost went up. Why did ordering cost go down? Well, it's because we're not ordering as frequently, because we're ordering more at a time. Holding cost goes up, which again should not surprise us because I'm holding more stuff in inventory for a longer period of time. That drops us down to $24,725. At $475, we have to order 2,000. Our product cost goes down to $23,750. Ordering cost drops again to $122.50, but holding cost goes up to $950, and we're at $24,822.50. And then step 4 is the easy one. Pick the smallest. Yay! It's ordering 1,000 cars at a time for $24,725 in annual cost. So we do save some money by ordering in bulk because the holding cost only jumped up by $130 while Well, the product cost dropped by 1,000.